Hi everyone and welcome to today's Daily Booster, which is number 6 today. First thing to start us off with then is our daily formula. So today's formula is for energy. Energy is of course measured in joules, and to calculate it we're going to use charge, which is measured in coulombs, times the potential difference measured in volts. Today's Biology Blast, we're going to have a look at genetic engineering. Now, genetic engineering is one of those processes which is more modern, and we're going to use it to produce these bacteria particularly, which we can then use to produce useful substances for us. So we can use genetically engineered bacteria to make things like hormones, like insulin. We can use them to make antibiotics and vaccines. So 3 very useful things that we can do. And the key thing that we need to know is how we do this. And there are 3 main steps to remember. So step 1 is we're going to identify the genes that code for that particular characteristic. Step 2, we need to remove that gene from the donor organism. And step 3, insert the gene into the host organism. So that's the kind of brief overview, if you like, of those 3 key steps. If we now look at a bit of detail associated with it, we need to know the names of the different enzymes involved. So when it actually comes to cutting the gene, we use this thing called a restriction enzyme. So what we're actually going to do there is use a restriction enzyme to cut the donor DNA at very specific base sequences. And when we do that, we leave these things called sticky ends. We use that same restriction enzyme to cut the bacterial plasmid DNA, and we will then have complementary sticky ends to our gene. So by using the same restriction enzyme with both the donor DNA and the bacterial plasmid DNA, we get complementary sticky ends, so the gene can join with the plasmid. To actually make it join, we use another enzyme called a ligase enzyme, which then joins our donor gene to the plasmid by joining the sticky ends together by forming a bond. We then get complementary base pairing through the action of another enzyme whose name you don't need to know for GCSE. So restriction enzymes do the cutting, ligase enzymes do the joining. It's all good and fine doing this process, but we need to know that it's actually worked, that that gene has attached to our bacterial plasmid. And we have 2 ways that we can do this through the use of marker genes. We can either use antibiotic resistance genes, or we can use fluorescence genes. If we consider the antibiotic resistance gene first of all, we insert a marker gene for antibiotic resistance into the plasmid at the same time that we put the gene we want for our characteristic in. We then put our bacteria onto an agar plate that contains that particular antibiotic, and we leave it to give it time to grow. If we have colonies present on that agar, then they must have that marker gene, the antibiotic resistance gene. And if they picked up that, then they picked up the gene we intended them to as well. So any of those colonies present have the genes we wanted them to. The second option is to use a fluorescent marker gene. First step, exactly the same. We insert our marker gene into the plasmid at the same time as our desired characteristic gene. We then transfer the bacteria to an agar plate, just as before. We incubate it and give it time to grow, same as before. The only difference is how we check the results. Because it's a fluorescence marker gene, what we do is we shine a UV light onto it, and then any of the colonies that glow have the fluorescence gene, which means they've got our desired characteristic gene. So don't forget that last step. Just to check that our intended gene has been taken up, we also add a marker gene to it and then incubate it, give it time to grow, and then we'll just test it using either obviously the UV light there or by growing on agar containing an antibiotic if it's the antibiotic resistance gene. Quick reminder of today's daily formula. Energy in joules is the charge in coulombs times potential difference in volts. For today's chemistry check, we're going back to C4, which is obviously on paper 2 still, but it's the first topic from paper 2. And we're going to look at the alkali metals, group 1 on the periodic table. Hopefully we remember the basic fact that group 1, the alkali metals, are something you don't want to mix with water or oxygen really, because they react quite a lot with both of those things. Because they're so reactive with both oxygen and water, when we actually store these metals, we store them in oil. Now, we store them in oil there, which is just going to prevent it coming into contact with oxygen and with water, therefore preventing them from reacting in storage. They are called the alkali metals, and this is not a lie in the name. They are still metals. Therefore, they have typical properties of metals. They are shiny when freshly cut, they are good conductors of electricity, and they are solids at room temperature. So typical metal properties there: shiny, good conductor of electricity, and solid at room temperature. We do need to know the trends as we go down the group. So as we go down group 1, we find that they get softer, their density increases, and their melting point decreases. So make sure you remember those 3 properties for group 1 as we go down the group. You also need to be able to describe the reactions of our first 3 metals, lithium, sodium and potassium. This should be an experiment you've seen in class. When we put lithium in our water, which you can see on the left here, it fizzed slowly. It was the boring one. It moved around slowly on the surface, just gently fizzing. Dull. Then we put sodium in, and sodium is in the middle here. When the sodium hit the water, it turned into a molten ball, and we can see it on that side there. That is actually a molten ball of sodium metal. That moved around on the surface quite quickly, and there was quite a lot of fizzing as we made that gas. And then our third and final one, our potassium, as soon as it hit the water, it burst into fire and it burnt with a lilac flame. It was zipping around on the surface really quickly, fizzing an awful lot, and also can explode. So as we see, these are getting more reactive the further down we go. So make sure you can describe those reactions. We could also be asked to write either a word equation or a balanced symbol equation for these. So the word equation, we've got the general one at the top. So metal plus water makes metal hydroxide plus hydrogen. The only thing we need to change is the word metal for the name of whatever metal it is. So if it was lithium, it would be lithium plus water makes lithium hydroxide plus hydrogen. If it was potassium, potassium plus water makes potassium hydroxide plus hydrogen. So if you learn the general word equation at the top, then all you need to do is just change the word metal for whichever alkali metal they give you. As far as the balanced symbol equation goes, if you memorize this, all you then need to do is change the symbol for the metal, because the alkali metals will always react in exactly the same way as one another. So for those of you that really hate balancing equations, here's a way around it. You can memorize 2Na plus 2H2O makes 2NaOH plus H2, and then just remember that if it was lithium, then all we would do is 2Li plus 2H2O makes 2LiOH plus H2. If it was potassium, all we do is we just change it for the K for our potassium. So you don't have to actually do the balancing yourself, because it will always be the same each time. Terrible, sorry, that's meant to just be a H there. So it's 2's in front of everything except for the hydrogen, because that is already diatomic. So 2 in front of your metal, 2 in front of the water, and 2 in front of the metal hydroxide. Easy to do, even easier just to memorize if you don't like balancing. The last thing we could be asked to do is to explain this trend in reactivity. And quite simply, this goes back to the number of electrons in the outer shell and how many shells there are. Because we're in group 1, then they all have 1 electron in their outer shell. So this means when they react, they're going to lose an electron. We know reactivity increases as we go down the group, and hopefully we know that if we picture the periodic table, there we go, this is going to be our periodic table. There's our alkali metals, so lithium, sodium, potassium, etc. Then what we actually have is, that's period 2, period 3, period 4, period 5, and period 6. If you remember from some of our earlier work, whatever period it's in, that is also the number of shells it has. So lithium will have 2 shells, and we can check that. It's got 3 electrons, so if we draw it, there it is. So 2 electron shells. Whereas by the time we're down at potassium there, it's in the 4th period, it has 4 shells. Each time, this outer shell electron is getting further from the nucleus. That means it's going to be lost easier because that force of attraction between the nucleus and the outer shell electron is weaker. So if you're asked to explain why the reactivity increases as you go down the group, it's because there are more shells, therefore the force of attraction is weaker between the outer shell electron and the nucleus, so the outer shell electron is lost more easily. Therefore, it's more reactive. Quick reminder of our daily formula then. Energy in joules is the charge in coulombs times potential difference in volts. For today's physics prep, we're going to look at gas pressure. Now, hopefully we remember the basics of gas pressure. If we have a container like a balloon, then there are air particles inside. Those particles are going to be moving. When they collide with the side of their container, we will have a small force created, and those collisions are creating gas pressure. So that's what gas pressure is. It's the small force created as air particles collide with the side of a container. Hopefully something quite obvious. If we have more air particles into a container of a fixed volume, then it's going to have an increase in pressure. So the more gas we put into a particular container, the higher the pressure will be, because we're going to have more collisions between the gas and the sides of the container, therefore pressure increases. We could also change the temperature. If we increase the temperature of a gas, we're giving those particles kinetic energy. So they're going to be moving around a lot faster. If they're moving faster, they're going to collide more frequently with the sides of the container. If they're colliding more frequently with the sides of a container, we get an increase in pressure. So increasing the temperature gives the particles more kinetic energy, therefore more frequent collisions with the container and an increase in pressure. Another factor we could change is the volume. So when we consider gas pressure and volume, they are what we refer to as inversely proportional. Now, what that means is that as one increases, the other decreases. But be careful on these questions, because quite frequently they will say something like, what will happen to the pressure if we double the volume? If you literally says it decreases, you're not going to get the mark, because where in the question they used this actual word like doubles, halves, quadruples, whatever it may be, you need to use a term that also gives a quantity. So if they tell you that the volume has doubled, then you would need to say the pressure would halve. Whereas if the volume had halved, the pressure would double. It's the opposite. The reason for that is that when we actually have our gas particles within our container, then we are going to have a lot more collisions if they're in a smaller volume. Just because obviously if you're packing the same number of gas particles into a smaller volume, then they're going to collide with the sides more frequently. So if we halve the volume, we're going to get twice the number of collisions each second with the container. Therefore, we will double the pressure. Hopefully you found our little daily booster useful today, and don't forget to come back again tomorrow for our next one.